Hi, in this video I'm going to go over integration and splitting in NMR spectrums. So first, integration. So integration tells you the number of hydrogens for each signal. So if I'm making an NMR down here, so this is my bottom line, I'm going to put in a couple signals here. So we got one right there, then one there. And what I'm going to go over next with the splitting, that will explain why the peaks look this way. But for right now, I'm more concerned about the integration. Okay, so let's say we have these 4 signals on our NMR. The integration is usually given to you. So say you're doing a problem on a test or a quiz, the integration will be given to you. Or if you're using an NMR spectrum, you just set one of the peaks equal to whatever number you choose, and then it integrates all the other ones relative to that one. So generally you'll want to pick a peak where you know what the integration will be. So say you're trying to make a compound and you know what it should look like, and you know what peak is going to correspond to what carbon and hydrogen on your compound. You can choose the peak that will say have 1 hydrogen on it, so that way you can choose that as the integration. So when you think of the integration, right, it's like the integral sign. Right, basically it integrates the peak and tells you how many hydrogens that signal has. So maybe this is 2, and this one's 2. There may be 3 hydrogens here, 1 hydrogen there. Right, it's not something that you can really calculate easily. It's something that the instrument will calculate for you. But the important part is it tells you the number of hydrogens for each signal. So when you're doing a problem where maybe you're given a spectrum and then given the formula of that, so say they're like, here's your spectrum and it's C4H8. You can use the integration to help confirm that the structure you make is the one that's corresponding to that peak. So there's not much more than that. This is just something that will be given, and it tells you the number of hydrogens for each signal. The one that's a little more challenging that you have to figure out is going to be the splitting. So what the splitting means is that neighboring hydrogens, so that means hydrogens on carbons adjacent to each other, split each other. I don't want to go too in depth into the quantum chemistry behind what the splitting is. For our purposes, I want to more just show you how to identify what the splitting should be in a compound, and how to identify that splitting on an NMR spectrum. So I'm going to draw here a compound that has every type of splitting that you'll see. And that way we can go through each of the types of splitting with the same sample molecule. So this is our compound here. The first type of splitting I'll do in blue, and that is a singlet. So a singlet means you have no carbons with hydrogens adjacent to your signal. So the singlet here would be right there. The 3 hydrogens on that carbon are the singlet. So the integration would be 3, and you'd have a singlet there. What a singlet peak looks like is just straight up and down. The formula for determining what the splitting is you're splitting, got an extra dot there. So your splitting is equal to 1 plus n. N is the number of hydrogens on adjacent carbons. So in this case, for the first one, the splitting is 1 plus 0 to give you 1, which is a singlet. So next one I'll do in red, and that's going to be a doublet. There's going to be 2 doublets in this compound. Right there and right there. They're doublets because there are 2 hydrogens here, but they're identical, so they count as the same signal. So it's 1 plus there is 1 hydrogen on that carbon adjacent to it. So it's 1 plus 1 to give you 2. Same thing with the one right here. It has 1, right? This is the carbon we're on, and the adjacent carbon right there has 1 hydrogen. So that gives you 2. So next up is going to be a triplet. Last thing about the doublet, the peak is going to look like that. The heights will be identical or virtually identical to each other. The triplet means that you have a neighboring carbon with 2 hydrogens on it. Or you have 2 neighboring carbons that each have 1 hydrogen. So the triplet here is going to be at the end over here, because the carbon next to it has 2 hydrogens, so it would be 1 plus 2 to give you 3. A triplet peak looks like that. The peak in the middle is taller and then has 2 symmetrical shorter peaks next to it on either side. Number 4, if you're following the pattern, is going to be quadruplet now. On this molecule, there is 1 quadruplet right there. That signal is a quadruplet because it's 1 plus there are 2 hydrogens there and 1 hydrogen here. That adds up to 4. So that gives you your quadruplet. What a quadruplet looks like is 2 sets of symmetrical peaks. The top 2 in the middle are symmetrical and taller, and then you have the 2 to the side that are symmetrical and shorter. Then lastly is going to be the multiplet. So multiplet. What a multiplet means is it's 5 or more. Sometimes you'll see it as, it'll be a heptet or a sextet, right? That's indicating to you exactly how many hydrogens are splitting, but in general, it's difficult to determine just from looking at a multiplet how much splitting there is. It just kind of looks like, multiplets are often just going to kind of look like something like that, right? It's hard to see exactly what it is. You just know that it's more than 4. And that's really all you need, right? You don't need to know exactly how many. In this, there are 2 multiplets, right there and right there. So we'll call this one 1 and multiplet 2. So for multiplet 1, it's 1 plus there are 3 hydrogens there and 2 hydrogens there. So this gives you 6 as your number. Then for multiplet 2, you've got 3 right there, 2 more to the right, and then 2 more, those red hydrogens right there are all adjacent. So that gives you 8 as yours. So that's why both of those would be multiplets. So again, when you're looking at an NMR spectrum, you want to look for what the shape of the peaks are. That will tell you the splitting, and that will help when you're then constructing your molecule from the NMR you're looking at. It'll help you determine where the bonds are, what type of bonds you'll have, right? If you have a singlet, it has to be some sort of methyl group. It can't be splitting anything, right? So you have to figure out a way to have a methyl group that's not splitting anything. That's generally what your singlet peak will look like. There's common patterns as you do the problems where you'll have a doublet, and if you have a multiplet and a doublet, that often indicates you might have like an isopropyl type group, because you have your multiplet, like we do in this one, number 2, multiplet number 2, right? That's often going to be an isopropyl group that has a doublet right there, right? So those are patterns that you can look for. And in the final video in this series of NMR, I'm going to go through a couple of practice problems with NMRs, and we'll be able to see how we can identify those patterns and construct our molecule from the NMR spectrum.